Assalamualaikum and good day everyone. We are Group 1 and today we will present our project on computational modeling and design optimization of the ion implantation process using extreme T-ring simulation. This slide introduces the fundamental physics of ion implantation. Ion implantation is a controlled process used to introduce dopant ions into a semiconductor wafer. During ion implantation, dopant atoms are ionized, accelerated, and implanted into a semiconductor wafer, where they lose energy and come to rest beneath the surface. The ions lose energy through two mechanisms: electronic stopping at high energies and nuclear stopping at lower energies. In crystalline, silicon ions may also undergo channeling, causing deeper penetration. This effect is minimized using wafer tilting, rotation, or pre-amorphization implantation. This slide presents the design of experiment. All simulations were performed using extreme T-ring 2013 with a stochastic set of 1294 ions per run. Two target structure, pure silicon and 2 nanometer silicon dioxide on silicon were investigated. The study consisted of 3 parts. Part A verified the simulation. Part B compared the target material using quick calculation and full cascade. And Part C optimized a full-stack boron implantation recipe.
Figure 1 show the range geometry dynamic for boron 11 and arsenate certified in silicon. You can obviously project the range and lateral struggle expansion of energy. Boron, shown in blue, penetrates much deeper than arsenic, shown in light blue, reaching approximately 215 nanometer at 200 kV compared to arsenic 100 nanometer. More importantly, boron lateral struggle, shown in green, is significantly larger than arsenic, reaching about 60 nanometer compared to only 30 nanometers. This large lateral struggle is critical because it causes the doping profile to spread sideways, reducing the effective channel length in sub-micron transistor. For a 90 nanometer design, boron lateral spread can shorten the channel to just 20 nanometer, triggering reserve short channel effect. Figure 2. Compare electronic and nuclear stopping power for boron 11 and arsenic 75 in silicon. For boron, shown in blue, electronic stopping is higher than nuclear stopping across all energies. This means boron loses most of energy through collision with electrons. For arsenic, shown in red, nuclear stopping dominates at lower energy, but electronic stopping takes over at higher energies. The crossover occurs at approximately 75 to 100 keV. This difference is due to the mass. Boron is light, so it interacts more with electrons. Arsenic is heavy, so it transfers more energy through direct collision with silicon nuclei. The crossover point is important because it determines whether the ion creates more lattice damage or more ionization, which affect the device performance.
For Part B, we analyze our lattice displacement profiles under full cascade mode using our verified 1294 ion stochastic seed. Looking at Figure 3, 100 kV arsenic creates an intense narrow defect profile near the surface, yielding a peak vacancy density nearly an order of magnitude higher than boron. Boron conversely distributes its structural damage much deeper and broader across the target grid. The core physics driving this variance is that 70 to 85% of these vacancies are caused by knocked out target atoms acting as secondary projectiles rather than the primary ions. Figure 4 maps this energy partitioning matrix. At lower energies, nuclear stopping power dominates, channeling kinetic energy directly into target phonons and displacements. As beam energy scales upward, the systems transition into the electronic stopping regime, maximizing target ionization according to the breeder block principle. However, high nuclear stopping introduces severe boundary risks, as shown in Figure 5. When arsenic passes through a protective 20 nm screen oxide, its heavy mass triggers dense secondary recoil cascades near the interface. This forward momentum violently knocks native oxygen atoms across the heterostructure boundary, injecting a destructive oxygen recoil tail up to 10 nm deep into our pristine silicon channel. These impurities act as scattering centers that degrade channel mobility. Quantifying these spatial boundaries is critical for optimizing our subsequent Thermal annealing window to secure our final wafer lot yield.
For Part C, our science scenario is the design of a boron 11 implementation recipe for a high-frequency NPN-BGT base layer. The target doping region must be located between 100 and 250 nanometers below the silicon surface. The required target concentration is 4 times 10 to the power of 17 atoms per cubic centimeter. Since the tolerance is plus or minus 10%, The accepted concentration range is from 3.6 times 10 to the power of 17 to 4.4 times 10 to the power of 17 atoms per cubic centimeter. The implementation energy must also stay within the hardware limit, which is between 10 and 80 kiloelectrovolts. The most critical constraint is the leakage boundary. At 350 nanometers and deeper, the boron concentration must not exceed 4 times 10 to the power of 15 atoms per cubic centimeter. Therefore, the optimization challenge is to form a box-like profile while preventing the boron tail from extending too deeply into the silicon substrate. The final recipe uses 4 boron-11 implementation energies, which are 30, 40, 55, and 70 kiloelectrovolts. The normalized boron profiles were extracted from the SRAM range output files. Each profile was then multiplied by its selected implant dose. The doses used were 2.76 times 10 to the power of 12, 1.00 times 10 to the power of 11, 4.90 times 10 to the power of 12, and 2.15 times 10 to the power of 11 ions per square centimeter. After that, the 4 scale profiles were added together to form the final cumulative concentration profile. Figure 6 shows the individual implant profiles and the final superposition profile compared with the target box and leakage boundary. This final recipe was selected as the best leakage-safe industrial trade-off. A higher 70 kiloelectrovolt dose could improve the deeper side of the target window, but it would also increase the boron tail beyond 350 nanometers. Therefore, the final recipe reduces the 70 kiloelectrovolt contribution and prioritizes the leakage control while still maintaining the closest feasible box-like profile.
Hi, I'm NAILI SOFIAH HAZLAN and I'm going to talk about the discussion of this project. The overall result showed that iron mass strongly affect implantation behavior. Boron is a light ion, so it penetrates deeper into silicon and produces a wider straggle. This makes boron useful for forming deeper dope region, but it also makes the profile harder to control. On the other hand, arsenic is heavier, so it experiences stronger nuclear stopping and produces more localized lattice damage near the surface. Another important point is the limitation of the SRAM itself. SRAM assume an amorphous target structure, so real crystalline channeling effect in silicon wafer are not fully represented. In an actual fabrication process, wafer tilt or pre-amorphization may be needed to reduce channeling. For Part C, the main optimization challenge was balancing profile flatness with leakage suppression. A higher deep energy dose can improve the box profile inside the 100 to 250 nanometer target window, but it also increased the boron tail beyond 350 nanometer. Therefore, the recipe was selected as the best industrial trade-off because it prioritized the leakage control while still maintaining a reasonable box-like profile. Alright, next, for the conclusion part, SRAM or TRIM was successfully used to model ion implantation behavior in silicon. In Part B, it shows how boron and arsenic differ in projected range, stopping power, lattice damage, and interface mixing. In Part C, it demonstrated how multiple boron implantation steps can be combined to form a box-like doping profile for the NPN-BJT base layer. The final selected recipe represents the best trade-off between uniformity, voltage limit, and leakage control. That's all from us. Thank you.